Lanthanum, although hard to say, is a not often talked about, but an extraordinary element. It is used in numerous commercial applications and is essential trace element in both plants and animals. I will be calling it Moly-B for short. The objective of this presentation is to instruct AP Chemistry students about the definition and identification of transition elements. They will also be able to write electron configurations for atoms and ions and describe the characteristics and structures of alloys using Moly-B as an example. The last two objectives are from the 2019 AP Chemistry course and exam description guide. Moly-B is a period 5 transition element that is typical of most metals with a silvery white and shiny finish. It has an extremely high melting point, actually one of the top 5 metals, and that makes it a valuable additive in the formation of many alloys. A transition element is often considered all the elements in the D block, and the lower transition elements are in the F block. But some of these metals are omitted if the definition of transition metal is strictly followed. This next video clip will describe how to write an electron configuration and run Moly-B through the paces to see if it meets the criteria of a true transition metal.
Transition element, by definition, contains an ion with an incomplete d orbital. So if we take a look, the d orbitals you can see are in the middle. So to help us figure this out for MO, is we need to write its electron configuration, which shows us the arrangement of electrons in the atom. To write the electron configuration, you'll notice that I have rectangles around the completed orbitals. And so you continue across the periodic table until you hit the element that you want, but you stop and record at the end of every completed shell. So if we start, we're trying to get to number 42. If we start, we're going to start at hydrogen. We don't stop there. We stop at helium. And we look at the little numbers. The numbers on the outside is period numbers, shows us the energy level. And so I know that helium is 1, and then its orbital is s, because it's in the first energy level, only has 2 electrons, so 1s2. And so we write that down. So we're going to write down 1 S2. And then we just continue along until we get to MO. So our next stop is beryllium, which is going to be 2 S2. And then neon, 2 P6. Magnesium, 3 S2. Argon, 3 P6. And then the grid for calcium is 4 S2. Then we need to take a pause at zinc because on top of the d orbitals I have an n-1. That means the d orbitals, the electrons are actually going in an inner shell. So what I take a look at is, oh, it's the 4th energy level, but 4 minus 1 is 3. So it's actually going to be 3 D10. Then back up again is Kr, which is 4 P6, and then Sr, 5s2. And we don't go all the way to CD because we just need to stop at MO. And so MO, again, we look at 5, so 5 minus 1 is 4. So it's going to be 4 D and then 4. Well, that's a whole lot to write down, and as you get down further in the periodic table, it's a lot to write and a lot to look at. And what really matters is those valence or outer electrons, the last electrons that entered the that make up that atom. And so we can write what's called a noble gas notation. And so what we do is we take a look at the element that we have, MO. We find its noble gas, its last noble gas that we passed when we wrote the electron configuration, and that's Kr, which has 36 electrons. And so if we take a look, that's all the way to 4p6. So if we added everything up, you'd notice that it does equal 42. So we have 10, so 2, 2, 6 is 10, 2, 6, 2 is another 10, so that's 20, 30, and then 38 and 4 is 42. So if we stop and we just write down, we package all that for up to 4p6, and we just put that in brackets, and we call that Kr. So then what really we can focus on then is that last part of the story. So 5s2, 4d4. So the deal though with molybdenum is that really is not, it's a little exception to its electron configuration. And what's going to help us see that exception is that if we draw out the orbital filling diagram. So the orbital filling diagram shows us the electrons. Usually we do this vertically, but just to save space, I'm going to do it in a linear fashion. So I'm going to put 5s, and I'm just going to draw one line to represent that s orbital because there's only one. Now D's come in packages of 5, and so there are 5 d orbitals in that fourth energy level. And what we're going to do then is represent those exponents, which are electrons, by arrows. And so the first two we're going to draw, and then we're going to put these 4 in, but according to Hund's rule, we're going to just go straight up and down. Now the Aufbau principle basically says they fill lowest energy first. Hund's rule is that when they have equal energy, they don't pair up until they basically have to. But what we notice that for Kr is that because of the repulsion that occurs here on the 5s, that one of these electrons actually moves. And so we rewrite this electron configuration as 5s1, 4d5. Now this happens in a few places as we go along. It'll actually happen with copper and become like 4s1, 3d10. So we just have to look and see what happens with the energy. We just can't follow this algorithm. There's exceptions to think through. But back to our first original question, is MO a transition element, which means does it have an ion that has an incomplete D? So the element has an incomplete D, but does its ions? And so a typical oxidation number for MO is +6. Well, how does it get that +6? It's easy to see. It just loses all those valence or last electrons. And so in that process, what happens is that it would just basically be the electron configuration of Kr. It would be isoelectric with Kr. Well, that wouldn't make it have any incomplete Ds, and so it would not be considered a transition element if that was its only oxidation number or if it's only ion. But what we find is it does have some other common ions. One is +4. Well, what happens in +4 is that it loses the one from the S and then an additional 3. Now, in transition elements, or the ones that are filling the d orbitals, it loses the ones from the S. Even though it is not added last, it comes out first because it is the outer shell. And so it will lose that and an additional 3 other ones because +4 means to lose 3 electrons. And so when that happens, we're going to end up with 4d2. And another one is +2. And so what happens there is it, again, will lose the ones from the S first. And so we end up with 4d4. Well, both of those situations, notice that they don't have 10 electrons, which is a complete D, would make it a transition element.
So a quick correction, in the video it stated that +4 meant to lose 3 electrons, and what I meant is that +4 loses 4 electrons. Moly-B's property of high melting point, low thermal expansion, and resistance to corrosion have made it an ideal material for alloys that are used in areas that will meet extreme conditions. For example, the nuclear power plant and the aerospace industry and defense. Now, Moly-B will form substitutional alloys with other transition metals such as tungsten, rhenium, and tantalum because they have similar properties. And some interstitial alloys are also made by inserting carbon and oxygen into the spaces created in the substitution alloys that will further strengthen the material. To learn more about alloys, this POGIL, which stands for Project Oriented Guided Inquiry Lessons, is available for students. This is in the AP POGIL book. And it helps them to learn about how alloys are made and their properties. And then working in teams, students discuss the models presented in the POGIL to make their own meaning. This chart shows the many applications of MOLY-V based on its properties. As you can see, its durable properties make it desirable materials for use in these extreme conditions, such as the halogen lamps and the liquid metal and glass processing, which requires an extremely high temperature material. In addition to the alloy POGIL, there's an electron configuration POGIL, which is a great resource for introducing this concept to first-year chemistry students or AP chemistry students who did not have a first-year chemistry experience. This is found in the POGIL activities for high school chemistry. Another great strategy is to get students engaged in in asking questions, and doing this through the question formulation technique. So through the writequestion.org, teaches you how to have students process information, giving them a phenomena or possibly even a chart like the information that was on the previous slide. Then students will go through that process to generate questions, revise and prioritize their questions, and then turn that process into research. There are many professional organizations that you can visit their websites. The American Chemical Society has lesson plans and a lot of research on different types of chemistry. Also, College Board AP Chemistry, IB Chemistry, and there is even an International Molybdenum Association, and then the National Science Teachers Association has so many ideas, storylines, and best practices in how to teach chemistry. There are many scholarly resources from studies on the extraction and the effect on the environment to alloys and new technologies available. Thank you for listening.